Okay, in the last video we talked a little bit about 2D arrays. And so in this one I'll show an alternative to the 2D arrays that start to use the attractors. So in this case we're going to create a 2D array, but we're going to use some of the standard tools that we have available in Grasshopper. So if you look under the vector tabs, you'll see a couple things that are available. One, we have grids. So we have hexagonal grids, radial grids, rectangular, square, triangular grids. We also have fields. And if you think of fields, you might think of, say, magnetic fields, where you can, say, have positive or negative charge magnets, and that would control sort of this field of, in this case, vectors or tensors that would control directionality within the field. So we're going to take advantage of those and try to create our own sort of array to respond to point locations and how that might warp or change this field in different ways. So I'm going to start off, I'm going to use, let's pick a hexagonal grid. So I'm going to make it, in this case it has a plane, just an XY plane, a size of 1, an extent we'll make 25 in the X and Y direction. So something like that. Okay, so this gives you individual cells and center points of the grid. And I'm going to make a sort of a plane around that. I'm going to do that with a bounding box. And take all of these cells. And you can do that per object, which puts like a little box around each one of these. I'm going to right click and say union box. And I'm going to flatten these so it makes one big box around the whole thing. So since this is a planar grid, it's just going to be a flat box. And then the other thing I'm going to do is randomly distribute points around this surface that I can use as attractor points. So in this case, I'm going to use a command called populate 2D. Put that region in. This is how many points do I want. Let's choose something like 15 points. You can see that those spread throughout that object. And the other thing that you can change right now is its level of randomness, but how it picks the random points. So that is called a seed value. So because it's developing that randomness computationally, there's actually an algorithm that sort of approximates a random distribution of points. And so we can pick different numbers. Each number will have its own associated random points. But if they were the same, if you change that seed value, you'll end up with different point locations as well. Doesn't really matter, but just so if you want to change those in some ways, you can include that. So I'll have all of these as points. I'll turn off some of this stuff for you all, and you can see those point locations. I'll go ahead and group these as grid and okay, so from here I'm going to try to build a field of values that are associated with the positive and negative values of of the system. So one thing I need is if I go back to here under the field value, you can see you can add a charge to the field by line, by point, spin force, vector force, all of these things. And you can break a field or merge field together. I'm going to add a point charge. So I have these points. I plug them in. You can see that there's these little arrows that say, we're affecting this field in this way. Okay, and then I also want to, since they're kind of in plane, I want to affect them three-dimensionally as well. Let's come back to that. I'm gonna try to see if I can visualize that in some way. So these are all individual fields with this one element. Let's merge these fields together into one sort of field with 15 elements. And then let's go up here and see if we can evaluate this field. So I want to see what's happening around these points to this grid. So in this case, what points can we use? Well, we can use the points of these cells, maybe. These cells. I can say, let's get this continuity of these cells, which will basically give me the points around each one like this. I can plug those points into P. And so that gives me tensors, a field of tensors, and their strength. So the tensors are basically vectors, and the strength are basically the amplitude. So if you remember from the last video, we displayed some of those things. So we'll so from each one of these points, I'm going to show these. So you can see around each one of these points, they're pushing vectors out from each one of these. All right? So how can we use that to actually affect this field in some way? Well, if we have these points, we can try to move them. So I can move each one of these points by a certain vector. And then I can recreate those points. I'm gonna turn off this other stuff behind here so I don't see it. You can see they're doing some pretty crazy stuff. Like some of these points are jumping all the way over there. Some of them are jumping all the way over there, but in general they're all moving away from wherever those points are. So let's try to control that a little bit. So maybe we can limit how far it's jumping. So we have the strengths of these tensors. We can maybe set a minimum so it doesn't go too high. Let's go 0.882. Let's get those. We'll plug that into the move. No, it didn't like that. Oh, right. So that number is a value, but what you need is the vector. So we actually need to give it an amplitude. So this vector, I'm going to sort of scale down to whatever's smallest. So what this does is saying any of those large ones, compare it to this number, and whichever is the minimum number, then move it that. So when it gets really big, as you saw before, so if I plug this in, it's exactly like it was before. It has that vector with this amplitude. I'll visualize that so you can see this is how long those vectors are. Some of them might get really long in some cases, but they're all not so bad. And this is the vector direction, so you can see that information very specifically. And then I'm using the minimum just to control how far that goes. Alright, so some of these things are starting to be affected, but there's a limit to how far they can be affected by these points. So I'll try to make some room for these. Getting a little spaghetti-like. Clean up so you can try to see everything. Okay, what else might we want to do? Well, since these points are all in plane, they're only really affecting that grid in plane as well. So let's see what happens if we move them out of plane. So I'll come in here. Now I'll say, okay, we have 15 points. I want to make a random vector up and down and move those points randomly. Doesn't really matter to me, but just off of the XY plane. So if you type random, you'll get this little cat sitting in a box, which seems pretty random. And it'll have a range as an input. It'll ask how many numbers in that range, and a seed. So it'll give you one random point in between 0 and 1 with a seed of 2. So we don't want one random point. We actually want 15 random points, or however many points you have in this list. So we can say list length. I mean 15 random points. Yeah, 15 points. And we can set a domain. Construct domain. Put that in. And then we can say maybe we want to go -3 to +3. So we should have random numbers between -3 and +3 for each one of those points. So, and then we're going to move it in the z direction. If it's negative, it'll move down. If it's positive, it will move up. And we're going to move these points. These points by this value. You can see it already had some that jumped up, some that jumped down. You can plug that back into there. So this is our move. I'm gonna make that a section. Hide some of these things. You can also see it starting to affect the field. So it's pushing everything away. So the ones that are below are pushing it up. The ones that are up should be pushing it down. Another thing we might want to do is change how much it's affecting the field. So that's very slightly affecting the field. Obviously, we can turn that up more or less with that. At what point this one's probably sitting right on top of that node, so it's really close and affecting it a lot. Even at the threshold, which that starts to do that, these aren't really moving that much. So maybe we can say each point has a bigger charge. It's affecting the field more. So how can we do that? Maybe we'll add new random values as well. For each one of these charges. So you can add the charge right here. So I'm going to copy this random cat and the domain. Oops. And down here. I still want 15 values coming out of there. And maybe I turn this up. So I'm going to go say negative 100 to 100. And so that value can actually go in the charge. Instantly you can see that this is already starting to squeeze and pull that array or hexagonal grid much more than it was before. So now you can see the effect of this minimum is actually working pretty well, or I can say, okay, don't get too much. I can tune it to some point. And it's starting to pull it up out of plane, down a little. That happens more or less depending on how I pull those around. So I'm going to add these to this one as well. I'm going to have the field over here. And that is a basic attractor point in the field. Something else that you might want to put into that is maybe you want to show those vectors more specifically. So instead of using the vector display, I'm going to use this vector display. It's essentially the same thing, but you could add different colors and widths to the vector lines. So in this case, I'm going to take these original points, take the vectors. You can see that those pop up. I'm going to give it a color, and so we gave it colors before up here by using the hue, saturation, lightness. Let's try to do colors a different way. I'm going to say pick the gradient tool. The gradient tool will essentially feed in a value, and it'll try to map it between 0 and 1. So ideally that color will be between 0 and 1. If it's not, it's too high, it'll just be all the way to 1. If it's too low, it'll be just to 0. And these colors represent that range. So right now, we have these sort of values coming out of the tensor lengths, right? We can plug these values into the T. You see, all of them are almost all the same color, so they must be pretty high, or at least above 1. Let's see what the bounds actually are of that. 2 and 4. I'm gonna flatten this list. Okay, between 0 and 288. So that's a big range, much higher than what we're looking at here. So we can do one of two things. We can remap these numbers between 0 and 1 so they kind of find the scale, or we can change the upper and lower limits of this. So we know that 0 to 288 are the upper and lower limits. We can deconstruct domain. So we have the 0.43 and the 288. So we can plug those in. So I'm not super happy with that. It looks as if maybe some of those high numbers are really skewing everything, and everything might be within a certain range, really. Maybe it just has like 288, this one up here, that's this dark red color, but then everything's basically in that. So I'm gonna, let's see if we can artificially turn that dead. So you can see at some point that's starting to give a broader color range. If we wanted to really map those, maybe we say a maximum or a minimum on this as well. We have some say on how that color is affected. And this red and pink is not that great, so you can actually you can put in different colors as well, or if you click on this little rainbow thing at the top, right click, presets, you can change that to have some different presets as well. So if I turn off this grid, underline grid, you can just have the vectors that are sort of pushing and pulling around there. Or you can show that grid as well. So I think I'll stop there for the fields. You can play around with that. You can try to use that as your arrays. Maybe trying out the different grid types, or some other variation of this to try to get some interesting things happening.